The Toronto team collected blood samples and prepared DNA, but needed major funding to complete the study. It was then that they heard from Sequana, a company founded to hunt down disease genes. Sequana financed the study, immediately provoking charges that the company was exploiting the islanders, who did not perhaps fully appreciate their role in Sequana's business strategy. Canadian activists calling themselves the Rural Advancement Foundation International claimed that Sequana was committing an act of biopiracy, violating the fundamental human rights of the people from whom the DNA samples are taken. Sequana claimed, in a move that was guaranteed to provoke more accusations of biopiracy, to have found 2 genes conferring susceptibility to asthma, but refused to reveal them publicly until the European patent application was filed. The genes are located on chromosome 11, and subsequent studies of heterogeneous mainland populations have confirmed a role for chromosome 11 in asthma. It would thus seem that the genetic factors underlying the high incidence of asthma on Tristan da Cunha are not relevant solely to the isolated inhabitants of South Atlantic islands. The storm over Sequana's biopiracy was nothing compared to the hurricane that was to envelop Carey Stephenson and his company, Decode Genetics, a few years later. Recognizing that it was tedious and inefficient to look for a different Tristan da Cunha-like micropopulation for every disorder, Stephenson reasoned that what he needed was an isolated island, but one with a much larger population, among whose members one could look for a number of disease genes at once. It just so happened that Carey Stephenson was born on such an island. Iceland is about the size of Kentucky, but its population of only 272,512 is 1/15 that of the Bluegrass State. The island was settled in the 9th and 10th centuries by the Vikings, who brought with them women kidnapped from Ireland during the voyage. Iceland offers several advantages for the enterprising gene hunter. First, the population is very homogeneous, derived almost entirely from the original settlers. There has been very little immigration since Viking days. Second, there are detailed genealogical records going back many generations. Many Icelanders can trace their ancestry back 500 years. This handy resource is supplemented by a detailed register of births begun in 1840 at the University of Iceland. Third, Iceland has had a nationalized health care service since 1914. So the entire nation's medical records are uniformly ordered and readily accessible, at least in principle. A Harvard neurologist, Stephenson was interested in genetically complex disorders, such as multiple sclerosis and Alzheimer's disease. Recognizing his own people as a nearly perfect population for genetic research, he devised a project to link the genealogical and medical records to create a database for gene hunting. Despite the project's worthy purpose, local privacy statutes stood in the way until the Alþingi, the Icelandic parliament, founded in AD 930, passed the law on a health sector database in 1998. The legislation authorized the creation and operation of a centralized database of non-personally identifiable health data with the aim of increasing knowledge in order to improve health and health services. In 2000, Decode was awarded a 12-year license to build and run the Icelandic healthcare database at its own expense in exchange for an annual fee payable to the national government. The genealogical component of the database contains information in the public domain, but access to the medical records database is more restrictive. Operating on a basis of presumed consent, information about people's health is entered into the database unless they take the initiative to opt out. the genotype component is most restrictive, relying on informed consent. Individuals must actively agree to give tissue samples for DNA extraction. Here's the hotspot. Although deCODE has a system in place to protect donor privacy, critics argue it is inadequate. Since a person's DNA must be correlated with genealogical and medical records, samples are not taken anonymously. Instead, the source's identity is encrypted. In theory, such encryption could be broken. Word might get around, especially in such a small population, that one family or another is carrying bad genes, opening up the possibility of gene-based discrimination. The deCODE project crystallized in microcosm many of the issues concerning genetic privacy that had been discussed rather more hypothetically elsewhere. Nevertheless, despite the controversy, most Icelanders were in favor of the company, viewing it as a means of combining a noble mission, fighting genetic disease, with the happy prospect of serious money swelling the country's small economy. Caught up in the excitement, many Icelanders invested heavily in the company, snapping up shares for as much as $65, long before deCODE was officially floated on NASDAQ. But the economic downturn has not been kind to biotech in general, or to deCODE in particular. At the time of writing, shares are worth around $2. Many Icelanders have been left to rue those heady buy days. Still, deCODE has undeniably brought money into Iceland through its lucrative collaborations with both Hoffmann La Roche and with Merck. But with the government of Iceland willing to provide a $200 million loan guarantee and the company forced to lay off a substantial proportion of its workforce, the financial reality is that deCODE may yet prove to be less of an economic boon to the country than had been hoped. The real test of deCODE, however, lies not in the vagaries of the stock market, but in the science it produces. Here, unfortunately, the commercial imperative of non- or delayed disclosure makes evaluation difficult. The company, we learned via press releases, is now carrying out linkage analysis on 46 disorders, including asthma, depression, cancer, osteoporosis, and hypertension. It has found linkage markers for 23 of these disorders, and it has isolated genes contributing to peripheral blood disease, stroke, and schizophrenia. But with few of the details published in scientific journals, it is too often difficult to distinguish science from hype. Still, deCODE has certainly shown itself capable of making useful contributions. In June 2002, deCODE researchers published a new map of the human genome with significantly higher resolution than that of the old Ceph map. In addition, the long-anticipated publication of the company's research on schizophrenia hints at a scientifically and commercially productive future for the company. Whatever the years to come hold for deCODE, it's clear that its overall approach, a three-way marriage of medical, genealogical, and genetic records for a well-defined population, has great potential. The company is, therefore, not alone in subjecting the population of a whole country to genetic scrutiny. Finland, for example, has a population of 6 million and notable incidence of some 35 genetic disorders, some unique, others simply more common there than in other European countries. The Finns have duly attracted considerable interest among human geneticists. Other countries, too, are leaping on the genetic database bandwagon. In April 2002, Britain launched its Biobank program, and the government of Estonia is promoting a comparable nationwide effort as well. Large-scale population studies like these will ultimately help us track down even the most elusive of genes.